Now we listen Pouya Shati that will speak about using the MaxSAT for learning optimal decision tree. So using a solver to do machine learning. Okay, you can go ahead. Thank you.
So yeah, I'm Pouya. I have my PhD from University of Toronto. I was supervised by Sheila McElraith and Eldon Cohen. Now I'm working as so they told me I should stand here. Now I'm working as an applied machine learning scientist at StackAdapt. We do advertising technology, and in there I work on bid optimization. I managed to find the work that's related to my PhD, which is a surprise. And yeah, I'm happy to be here. And today we're going to talk about the fact that I think Boolean is not too restrictive. And we're learning optimal decision trees with SAT. So previously, in our previous talk, we learned about SAT, MaxSAT, and we learned about all the solving technologies that are being used. This talk is more about applications. It's more about how we can use those paradigms to encode different problems, especially in cases where it doesn't seem like we can. So the outline is normal. It's motivation and background. I've divided the talk into two parts, basic parts and advanced parts. My idea was that, well, we can cover as much of the advanced stuff as we can. But I did a rehearsal last night, and it turns out we can do none, probably. So I'll encourage you to read the advanced part yourselves if you're interested, because I spent a lot of time making the slides. And lastly, we just do conclusion, of course. This talk is primarily based on my thesis, so I encourage you for proofs, formulations, explanations to see the thesis itself, and in there you can find references to appropriate papers as well. So you can see the work that's inspired my thesis. Okay, let's move into motivation. So we have these combinatorial optimization paradigms that are great. One rough way of kind of categorizing them into a spectrum is that on one side we have very rich syntaxes like CP, MIP that can encode all sorts of things. And on the other side, we have leaner syntaxes like SAT and MaxSAT, that the entities that they encode are primal. They just, in the case of SAT, it's just a Boolean variable. And the rule of thumb is that the more richer syntaxes can encode problems more naturally, but the leaner syntaxes come with faster solvers. There's, of course, many exceptions to this, but that's a very rough way of categorizing things. And SAT and MaxSAT, as we saw in previous talk, have really good solvers, but they just do Boolean. So we might not be able to use them in first glance. We, of course, can use them theoretically because they're NP complete, and any NP problem you have, you can do it in SAT. But that's just theory. In practice, the reduction can become so large, and it can become harder to solve than another paradigm that's more complex, but it's more naturally suited to that problem. So the question is, the dilemma is, if we try to encode a problem that looks non-Boolean into the Boolean setting, are we able to reap the benefits? Does it repay the effort? And my central claim in this talk is that, well, it's complicated, it's problem dependent, but I want to convince you that the answer is yes, in more cases than you would expect. And as a case study, we focus on learning decision trees because they are very important models. They are interpretable, meaning that they are sparse, simulatable, and modular. And many variants of learning decision trees are NP hard, and they particularly are concerned with non-binary data, complex objectives, and user constraints. So it would be, at first glance, challenging to encode them in Boolean. And just to give you a little bit of motivation about why are we even learning these models, we know that modern ML models do all sorts of great things, but they're usually black box, meaning that we cannot understand what's going on inside them, and they are unconstrained. So we have no way of enforcing certain behaviors onto them and with a guarantee. And these issues become limitations in all sorts of critical applications where safety is important, it's medical, it's regulatory, and all sorts of things. So interpretable models address the first issue. They reveal why a decision is made. In constrained models address the second issue. They allow us to specify constraints for them and enforce those constraints. And the literature shows that interpretability does not necessarily come at a trade-off with accuracy, and constraints can improve accuracy and also performance. So it's good that we can learn them. Okay, a little bit of background information, but I won't go into the detail of this. I just included in the slides, but I'm assuming everyone is familiar with variables, rules, clauses, formula in SAT. And as we, again, emphasized in the last talk, the off-the-shelf solvers for SAT solvers are pretty good. We want to be able to utilize them. And we also have MaxSAT, which maximizes the number of satisfied clauses. We have partial MaxSAT, where some of the clauses are hard, some of them are soft. And we have weighted partial MaxSAT, where we can have different weights for different soft clauses. And for this talk, we just use MaxSAT as a short for weighted partial MaxSAT. And a little bit of background information on decision trees as well. They are exactly what you would expect. You have branching nodes. Each branching node is labeled with a feature and a threshold. So when a point goes into the tree, it compares that feature of that point against the threshold. If it's smaller or equal, it goes left. If it's larger, it goes right. And we keep doing this until we reach a leaf node where it has a label, and the label in the leaf node is assigned to the point. And yeah, so they are interpretable, but that interpretability is, of course, dependent on the depth and the structure and the shape. And learning these decision trees in an optimal way, it's NP hard in almost all cases. And we also have two problems, machine learning problems that are fairly straightforward as well. They have the classification, which we're trying to label the data and minimize misclassification costs. And we have clustering, which wants to group the points so that within each group, points are similar, and between different groups, points are dissimilar. And the decision tree variant of these problems is that find a classification or clustering solution to this with some structural constraints, of course. And this is how the talk is structured. So we have the basic and the advanced part, which advanced part we probably won't go into. For the basic part, I made a decision to, instead of presenting each of my papers one after the other, I want to gather all the components that exist in all of my papers and present the components on their own. So we have structural encodings, like how should we encode the decision tree itself. And then we have the objectives, different objectives that we can encode, different user constraints that we can encode, and different techniques that we have for improving the performance. Now, theoretically, you can mix and match all these components in different shapes, but certain combinations make sense. And those are the combinations that appear in my paper. But in our talk, I thought maybe just do it component by component. And one thing, so if we start from basic, we start from structural encodings. Well, one thing I want to emphasize here is that these things at the bottom, so whenever they have color, it means we started a new component. And the good thing about starting a new component is that if you've kind of lost, if you're sleepy, if you're distracted, and you see the color parts at the beginning, you can start paying attention again. So I don't want to lose anyone. Whenever we start a new component, you don't need to understand everything else. It's all independent. So keep an eye out for these colored parts. Okay, so let's start with the first part of the encoding, which is the tree itself. What does it mean for us to learn a decision tree? So we know that when in an input, a structure is given. So for example, they tell us find the decision tree of depth 3. What we need to learn are 3 functions. First is, what is the feature that is chosen for each branching node? Second is, what is the threshold that is chosen for each branching node? And third is, what is the label that is chosen for each leaf node? So if you learn these 3 things, we learn the decision tree. And a little bit of a tangent before we go into the encoding of the decision tree itself is that in our case, we assume we interpret the labels of the leaf nodes in the clustering context as the cluster that those points belong to. Because different leaves in our tree can have the same label, we theoretically can have a clustering that is spread out between different leaves. And this is a flexibility that often comes with using combinatorial optimization rather than heuristic search. And I want to make the case that this flexibility is a good thing, and this is my example. So let's say we have this kind of data that a natural non-tree clustering would look like this. If we have the limitation that is that we have one cluster per leaf, we might end up with making this distinction here that's not natural because we want the clustering to look like this. But if we allow the tree to have the same cluster across two leaves, this would be more natural. So some heuristic approaches that are limited to one cluster per leaf might suffer from this. Okay, so the tangent is over. Let's go back to the encoding. And anytime you see mathematical formula, you're welcome to not go into it. I just included it for the sake of completeness, but we don't necessarily want to talk about the math. We just want to talk about the idea. So here, what is the idea behind encoding a decision tree here? Note that our main theme of the talk is encoding seemingly non-Boolean talks into Boolean paradigm. In a decision tree, the non-Boolean part, the non-Boolean part seems like this, branching on a numerical value. How can we encode it into Boolean? Again, you don't need to go into all the variables, but the main idea is these variables here. So this means SI of t, it encodes whether point I goes left at branching node t. So we are directly encoding the beta value, which is feature selection. We are directly encoding theta, which is label selection. But what we are not directly encoding is the threshold, because threshold is a number. Instead, we just know where each point goes at each branching node. So the idea behind encoding numerical values in Boolean is to not encode them, basically. So we just don't encode them. Instead, we encode the effect of them. We know where each point goes, therefore we don't need to know the threshold itself. And now I want to talk about the second label that I have in my slides. So up here, I wanted to group the ideas that I talk about into different family techniques. So the shadow encoding is the first family. Basically, the idea is instead of encoding things, encode their shadow, encode their effect. So here is the first instance of doing that. So just to elaborate a little bit on the idea, we have these points in this space. For each one of them, we know if they go to right, if they go to left. And if we know that, we don't need to know the threshold because we know it's somewhere here. So we can just, let's say, select the average or another heuristic, and that would be fine. So within that tree, for each point and each node, we know where it goes. Even if the node itself might not actually end up there, we still encode where it goes. And of course, we need to have well-formedness constraints as well, because we cannot have, for example, this one go to left, because the previous one is going to right. So we encode those things as well, and that's basically how we encode the numerical thresholds. And it's a good thing because if we don't encode numerical thresholds, we need to binarize our values. And in this example, we see that if we have, let's say, 4 values, we end up with 3 binary features. And if we have 100 different values, we end up with 99 binary features. And that can get out of control really fast. But if we encode the branching directly, we don't need to do these explicit binarization of values. Okay, and this is the full structural encoding. Again, don't look at the math, but this is the interesting part, that whenever a feature is selected, we encode the well-formedness of these splitting variables, and that allows us to have a threshold. Okay, so this next section is objectives. What are the basic objectives that we talk about? First is max accuracy. This is not really related to our talk, but I have to include it. So it's not encoding a non-binary thing into the binary paradigm. It's just straightforward encoding max accuracy, which means the soft clauses that we talked about, correctly classify as many points as you can. And whenever you claim something to be correctly classified and it's in a leaf node, the label has to match. So we need to make sure that it's meaningful. The second objective is pretty straightforward too. So in the previous case, we, let's say, had a depth of 3 and we wanted to get the best accuracy possible. Here, we want a perfect accuracy, but with minimum depth. So we start from a depth of 1. We see if there is a satisfiable solution. If not, we increase the depth of 2 and 3 and so on. So in idea is very similar to maybe the lower bound MaxSAT solving that we had in the previous talk. And it starts another family of techniques, which is iterative algorithms. So when you encode something into SAT, the 0 to 100 doesn't have to be fully done in SAT. You have the control over it. You can have an algorithm around your SAT encoding, and you can incrementally make changes to your encoding and try again and try again. So in this case, we're doing the algorithm of testing different depths. If we explicitly encode the depth objective into our problem, it might have been more difficult to solve because, for example, we don't know what depth should we start from. If we start from 10, it might give us a solution, but that might be a very difficult instance to solve. The last objective that I want to talk about, the first two were classification. This one is clustering. So in clustering, we have the notions of maximum diameter and minimum split. So maximum diameter is basically the largest distance that you can find within a cluster. And minimum split is the shortest distance that you can find between clusters. A good clustering has the maximum diameter minimized and the minimum split maximized. So because we want the clusters to be separate and we want them to be coherent. So optimizing these two things is a fairly common clustering objective that we can do. But the issue is, again, they are numerical objectives. So what does it mean for us to be able to do it in SAT? It's basically shadow encoding again. So if we sort all the pairwise distances in our problem and along an axis, we notice that some of the pairs are, for a given clustering, some of them are clustered differently, the red ones. Some of them are clustered together, the blue ones. And the max diameter is basically the very last blue line, while the minimum split is the very first red line. So if we simply increase the number of red lines at the end and increase the number of blue lines at the beginning, we don't need to know what the maximum diameter and the minimum split is. We just know that if all of these are clustered separately, then the maximum diameter should be somewhere around here, and the same for minimum split. So again, we're doing shadow encoding. We're not having access to those numerical values directly. We just know that these need to be separate and these need to be together. And well, it's kind of belonging to another family of techniques as well, which I call proxy optimization. So here we have these two objectives. And because we're doing shadow encoding and we don't have access to their value, we don't know how they are scaled against one another. Like increasing the number of these lines is not equivalent to increasing maximum diameter or minimum split by one value. So what we're doing exactly is proxy optimization. We're optimizing the number of these lines as a proxy for our maximum diameter and minimum split objective. Again, a little bit of math here that it's just basically indicator variables to encode whether those pairs are being forced to be co-clustered or clustered separately. And one other thing about this objective is that because our objective has two parts, it's not straightforward to come up with a combination of what are we exactly optimizing for this. So we end up getting a Pareto front, which are basically non-dominated solutions in a space of two objectives. So solutions that you cannot improve on both fronts. In two objective problems, we usually end up with the Pareto front. And the proxy optimization that we're doing here finds one Pareto optimal solution, but other Pareto optimal solutions might still exist. And like we might encode additional objectives or preferences to focus on one of them rather than the others. So that was the objectives. Let's focus on user constraints next. So the first user constraint that we talk about, again, I'll remind you that whenever this is colored, it's something new. First user constraint that we talk about are must links and cannot links. They exist within the clustering space. So let's say we have a clustering that looks like this. We have our MD and MS from before, but also for some of the pairs, we have these blue line, which means that the user wants us to cluster these two together. And we also have these red lines, which means the user wants us to cluster them separately. So it's a way for the user to express maybe their preferences or maybe their domain knowledge and expertise. And basically, we have to find the model that satisfies these constraints in addition to optimizing the objective. And it's semi-supervised because, well, to some extent we have supervision, but it's not like classified where you have just labels for everything. This is the math behind encoding must links and cannot links. The clauses themselves, if you look at them, it's pretty straightforward. It just takes time to get familiar with the notation. But one important thing is, maybe that's another technique, but I didn't want to come up with a name for it. We're using unary encoding instead of one hot for encoding what the clustering is for each point. The benefit of using unary encoding, which we'll see next, is that it makes it easier for us to do symmetry breaking, which we'll talk next. Okay, that was the only user constraint that I want to talk about. I didn't know the basic part just had one, but maybe that's the most important one. So performance is a bit more interesting because we do some fancy stuff here to improve the performance of our algorithm. So we have the encoding, it works, but how can we make it faster to solve? The first thing is approximation, and it's just the approximation that we have in any computer science problem. At the end, we want an epsilon that when we increase epsilon, we get better performance, and when we decrease epsilon, we hopefully get better quality or at least tighter guarantee on the quality. So in our problem, we had the MD-MS objective, but they are driven by pairwise distances, which we have a quadratic number of them. And we have a quadratic number of cases for MD and a quadratic number of cases for MS. So space of objectives is huge, which is something that we would probably want to avoid. But in practice, if we have a very small epsilon, and we have two solutions where maximum diameter is epsilon different from the other one, it's probably not that different. So we can apply this approximation idea here and reduce the number of possible solutions or possible objectives significantly. So remember the axis that we had where we sorted all the pairwise distances alongside it? We just need to group all of those lines into these boxes where every box, the width of every box is at most epsilon. And we consider all of the box together when we want to enforce it to be in the same cluster or in different clusters. And that just decreases the solution space significantly. So yeah, the axis would look something like this. We put these lines into these boxes and we just enforce the same thing for the box as a whole. And the proposition is, well, if you remember, we had, when we were focusing lines individually, we had these we claimed that it finds a Pareto optimal solution. But how does our epsilon approximation affect the Pareto optimal solution? And in order to have some sort of guarantee, we define this epsilon Pareto optimal notion, which means that, well, we're approximating the solution, but just like when we had one objective where we claimed that when we approximate the solution, we are epsilon far from the actual optimal value. In the Pareto sense, we say that it's in an epsilon neighborhood of the optimal value. So if we have these two objectives, let's say MD and MS, we have this Pareto frontier, we might end up with a solution like this, where it has a rectangle where a square of side epsilon, where we are guaranteed to find Pareto optimal solutions in that square. So it's just an extension of the notion of approximation to the Pareto setting. Okay, so connected to that, we start the next component that we want to talk about is called the smart pairs algorithm. So we talked about the fact that our by criteria objective MDNMS works with pairwise distances, so it might blow up. We also have ML and CL constraints. They might also blow up because they also work with pairs of points. And we have this observation that these two are closely connected because MDNMS try to put pairs into the same clusters and in different clusters, and ML and CL are doing the exact same thing. So they are heavily affecting one another. Is there a way for us to utilize this? And that brings us into another family of techniques that I want to talk about. It's pre-processing. So there's nothing in the books that says if you're doing a Boolean encoding, the encoding itself has to be super fast. It just has to be a surface level translation that's linear or polynomial, and that's it. You might actually spend some time doing some sort of manual calculation before you actually tackle the encoding to make the encoding as easy to solve as possible, or maybe as small as possible. But we have pre-processing, that's the general idea. And in this case, we have this smart pairs algorithm that does the pre-processing for us. And it works with the encoding, and it automatically detects when a pair of points are implied to be clustered together or implied to be clustered separately. And because of that, it tells us whether something that we're doing is redundant or infeasible. If you look at the example, let's say we've already added ML links between these two, and these two, and we have the CL link here. If we try to add an ML link between E and D, smart pairs algorithm tells us this is infeasible because D and E are already implied to be in different clusters. Or if we try to add a CL link between E and D, the smart pairs algorithm tells us that this is redundant. You don't need to add that because that distinction is already encoded. And well, it's simpler to think about it with regard to ML and CL, but it also interacts with our objective encoding, because in our objective encoding, we kind of, let's say we want to do MD. We start from the shortest pair of points and we start encoding their co-clustering in an objective setting. But even in that case, you might say, okay, you cannot put these two together. So you can stop encoding the MD objective at this point. So there are many different, maybe somewhat convoluted cases, but the idea is detecting redundancy and infeasibility. And as a result, we end up with an encoding that's significantly smaller, so it's easier to solve. Another idea is, well, this is really not related to the theme of our talk as well. It's not non-Boolean things into Boolean, but it's always good practice to have, is to remove equivalent solutions. So in the case of clustering, if we have an arbitrary clustering and we just rename the clusterings, we end up with an equivalent clustering. So we don't need to consider all of those solutions because for each clustering, there are k factorial equivalent ones. So we just add symmetry breaking clauses. The clauses themselves are a little bit more complicated here, but the idea is that it's just one of those equivalent clusterings that is a viable solution in our encoding. The others are just simply infeasible. So this is where the unary encoding helps us actually. The clauses look simple, but basically what it's enforcing is that when you are, let's say, considering the fifth point, it cannot be assigned to cluster 3 if cluster 2 has never been used in the first 4 points. So it's monotonically increasing in terms of the first member of each cluster. That would remove all the equivalent. Okay, so yeah, I have 15 more minutes. Maybe we can talk about some advanced stuff as well. I was faster than I expected. So let's talk about solved problems that we actually do. So as I talked about in the papers, I don't discuss these components individually. They are actually solving problems. Here, I thought maybe it's a good idea to present them individually, but there are certain combinations that make more sense than others. So we learn decision trees that maximize accuracy for classification, minimize depth for classification, and we also do constrained tree clustering with the by criteria of MD&MS and with must-link and cannot-link user constraints. And this is a particularly difficult problem to solve And in our paper, I believe in our specific case, we were the first authors to actually solve this problem. So we need to do a lot of fancy performance stuff to actually make this viable. You can, of course, have just ML links in the classification setting as well, because they are all just SAT. You can just put them together, but it probably doesn't make sense, or maybe it does, depending on your application. So these are just some of the valid combinations that we actually solved. And if we go into results, pretty much just it's good. So we compare against the baseline, we see that we if it's a case that we actually end up in an optimal solution, we reach the optimal solution faster. If it's a case where it's timeout, we get a better solution in that amount of time, because one thing that some MaxSATs can do is that they might time out, but they might give you a solution that's pretty good. It's not guaranteed to be optimal. So we see that in those cases, our approach also works better than some of the baseline, and the direct encoding of numerical values is a big part of that as well. And one other kind of byproduct of using SAT is, well, SAT is very memory efficient. Many off-the-shelf solvers are really good at using memory, as we saw in our previous talk as well. But let's say compared to a caching and searching approach, which might compare comparatively in a runtime and inequality setting, it does not compare competitively in a memory usage setting. So we use considerably less memory compared to some of the other techniques that were able to get comparable solution qualities. And that's just one of the byproducts of using SAT. And this is the graph that I'm probably most proud of out of all of my PhD research. As I said, the problem of learning optimal decision tree clusterings was never solved before. So we did it in our paper, and we also supported constraints. But, well, as a researcher, you always have to ask the question, why? Why do we have optimal clustering? And if we are enforcing interpretability into clustering solutions, does it going to make everything worse? And we have a good amount of information from the literature on the classification case, where interpretability comes, well, doesn't come, but it doesn't come at a cost to accuracy. We can find incredibly accurate interpretable solutions in many settings. It's not always the case, but in many settings it is. So the main question is, does that observation extend to clustering? Are we also able to find clustering decision trees that are of very high quality? And basically what this graph is telling us is that yes. So if we go into a little bit of detail, we have the CC clusterings that are basically just non-tree variations. We have three. We, of course, we also consider two objectives. One of them is just max diameter, and the other one is max diameter and minimum split together. The x-axis is the amount of constraints that we use. So, and the green bars are infeasibility or feasibility. So if we add more and more constraints, of course, it might be harder to satisfy all of them. So feasibility goes down, but the lines themselves are ARI, which is a metric for clustering accuracy. And we see that both three cases outperform their non-tree counterparts, that's the main surprising one, and that's the most important result. Well, we also see that MDMS outperforms MD, which is somewhat expected, and by adding constraints, we get a better and better solution. Well, we also see that for example, 3MD compared to CCMD, we see that 3MD goes monotonically better when we add more constraints, which means that it's able to utilize constraints much better. But the flat one actually dips at the beginning, which means that because of its lack of structure, it might not be able to, the constraints might not be meaningful to it. And we also see that even without constraints, the tree ones basically go up very fast. So with a minimal number of constraints, we can get really good solutions. Well, that might not be the case when we are considering non-tree solutions. And the kind of intuition behind it is that decision trees are structured, and for clustering, we can looking for a structured way of organizing points. So it's not it is a surprise, but it's not completely out of the blue that a decision tree clustering is actually able to reflect the internal structure of the data points very closely. And again, because of the structure, it's probably able to utilize the constraints much more effectively than a non-tree case. Because in a tree, if we, let's say, have a point from here to here, that means that, well, these are in the same rectangle. But in a flat case, if you have a point from here to here, well, all the points close to them might still have all sorts of arbitrary solutions. Of course, it's more complicated than that, but that's the intuition of why tree clustering works so well. And we, of course, have just the performance results as well. It's a bit boring. Just, oh, sorry. The smart pairs, where we prune the clauses and the encoding, and the epsilon approximation allows us much better performance and less clauses, less time, less number of failures, and so on. So I still have 10 minutes. Are there any particular ambiguities of the basic part? If not, I can start the advanced part and then we can go into some questions. Okay, so for advanced, again, we do the structural encoding, objective user constraint performance thing again, but these ones are more advanced. So the first advanced thing is the categorical features power set encoding. So if you remember, for encoding a branching, a numerical branching, we just encoded where each point goes. A very natural extension of that is to the case of categorical features. Because even if the feature that is selected is categorical, if we know where each point goes, we know what kind of categorical branching we're doing. We just have to change the well-formedness constraint so that there is no natural order between larger or smaller values, because everything is categorical, everything is one-off. And that allows us to come up with a power set branching, where, let's say, for a feature of f, you have 6 possible values. You can find a decision tree that branches on 3 of them, and it can just split the values right in the middle. But if we go again the route of binarizing things, we end up with a decision tree that has a one-hot binary encoding of the feature. So we might need a decision tree of depth 4 when you can actually do it with a decision tree of depth 2. So our way of encoding things in the categorical sense is not just pure performance benefits, but it also allows us to find much more expressive and compact solutions. Yeah, so the changes to the encoding is pretty small. We just have to update the well-formedness constraints. And we have the result that any tree that enjoys power set branching is more expressive than a tree that doesn't enjoy. It's pretty straightforward. And it matters a lot on certain data sets where, let's say, we have one feature that has 20 different values. In that case, the effect is significant. Next, we talk about another structure. So a new structure. Right up until now, we just talked about decision trees. But I want to talk about a more compact case as well. So in BDDs, binary decision diagrams, they are an oblivious relative of decision trees. And oblivious means that across a depth value, all of the branching nodes use the same branching. They use the same feature and they use the same threshold. And because of that, they are obviously more compact because the number of branchings is significantly reduced. But also having those equal branchings across the level allows us to just reduce the tree into a diagram. We can merge equivalent nodes, reduce redundant ones, and just make it as compact as possible. And yeah, so we can reduce it in many different ways and get many equivalent BDDs. But if we reduce it all the way, there is a theorem that it's unique. We only have one BDD. For each decision tree that we reduce, we only end up with one BDD if we reduce it all the way, up to renaming, of course. So it looks something like this. For For a decision tree that looks like this, here it's non-reduced, meaning that it's still a tree, and it's non-ordered, meaning that from the first one, the root, all the way to the leaves, in one path we see F1, F3, F2, in another we see F1, F2, F3. But if you reduce the value, the features that are selected in the branching nodes and merge and remove the redundant ones, we get something like this, that it's unique, it's ordered, and it's reduced. Okay, so how can we learn BDDs actually with these approaches? It's pretty straightforward. We just learn a decision tree first, and we enforce it to have equivalent branchings across each level. We just use the same variable for all the nodes. And after we get the tree, we reduce it and we get a BDD. So that part is pretty straightforward, and yeah, we just need some minor modifications to the variables. But how can we maybe go into the custom? Actually, I have 5 minutes. Let's not talk about this. This is probably a bit more complicated than the other one that I have. It's multi-dimensional BDDs, just to give you the name. Okay, I want to talk about this. So BDD size optimization. Okay, we learned the tree and then we reduced it into a BDD, but the main point of having BDDs is their compactness. So how can we optimize that front as well? The general idea is, again, another instance of the technique shadow encoding. So instead of encoding the structure itself, let's say limiting the number of points and encoding what the parent of each node is and how they're connected, and we can just end up encoding graphs, which is very costly. We encode what happens to a branching node during the reduction process. So the question is this node going to remain at the end after we do the reduction all the way through, or will it get removed? If we are able to have variables for those things, we can just optimize those variables as soft clauses or optimize those clauses. And as a result, optimize the size of the BDD as well, which of course we have to balance against the accuracy, because we now have 2 objectives, and there are different ways of balancing it. But the idea itself is just optimize the number of nodes that we think are going to get removed during the reduction process. And they can be removed for 2 different reasons. Again, the notation here is probably a bit difficult, but it can be removed either when its 2 children are equivalent. So AKA the parent node is redundant, the branching isn't meaningful, or it can be removed when it's equivalent to a previous node that appears in the same level. So if we are counting the branching nodes at level 5, and we see one point that's already equivalent to a previous one, we say, okay, I don't need this. So it's pretty straightforward in terms of why they're removed. And if we optimize that, we're optimizing the size. And yeah, again, the reduced counterpart. I don't want to talk about this. Actually, maybe just a quick glance. So we can also do the size optimization either at the same time of accuracy or in the second stage. We can optimize the accuracy first, and then we end up with a bunch of decision for leaves that don't have any points. So the labels of those leaves doesn't matter. They don't have any points. We can decide on the labels in a way that gives us the most compact size. So that's another way of approaching it. And that would be 1 stage against 2 stage. I want to see the results of this as well. We just have 2 minutes. So the very interesting result here is that, so as we go towards this side, we get more and more aggressive size optimization. So here we just have no size optimization. Here we have a 2 stage that is considered less aggressive than the first stage. Here we have a first stage with very high weight, and then we decrease the weight again and again. So we see that size keeps going down when we aggressively optimize it. But the interesting thing is the training accuracy plateaus at 10, and the testing accuracy kind of plateaus at 3. So it means that we can optimize the size a lot without actually hurting the training accuracy, and even more without hurting the testing accuracy. which is the surprising result of this paper. So I just wanted to share that as well. And now I realize that we are out of time. So the summary are these family of techniques: shadow encoding, don't encode the thing, encode its effect; proxy optimization, encode another objective that optimizing it is equal to optimizing your own objective; iterative algorithms, have an algorithm around your encoding so that it changes the encoding and tries again and again; approximation, which is pretty straightforward; pre-processing, try to do some calculations so that your instance is as easy to solve as possible. And we, of course, have plug-and-play encodings that I didn't get to talk about, but it's just get some encoding from somewhere, some paper, some library, and people have more improved encodings than for well-known problems compared to you. So for cardinality of strains, for example, just use an off-the-shelf encoding, and you can plug it right into your model. And just briefly, I want to talk about, well, why we want to use combinatorial optimization, and in this instance, SAT, for problems in machine learning. It's because they give us modularity. In this talk, we were able to mix and match all the components. It gives us guarantees. Heuristic approaches don't tell us this is an optimal solution, don't guarantee satisfaction of constraints, and so on. We can easily trade off different things. Like if I solve a SAT instance, I can just change the weights and solve it again. But if it's a heuristic, it might not be straightforward to balance things against one another. And it's scale. And this is particularly the case when we compare SAT and MaxSAT against other combinatorial optimization approaches, because they are incredibly fast and efficient. And yeah, I refer you to my thesis for details, and thank you so much, and I'll be happy to take your questions.
We have question.
So in your case, you're working on a fixed data set, and then you're trying to find optimal or near optimal representation for this data set. And I don't know if you look at this aspect, but I see at least two places where you could use your method for outlier detection. Like first, that you're working on the individual data in the data set. So you have clauses that will say this thing will be misclassified, or this will be too big. So in some sort of way, you could already detect, like, you may be able to get a very good quality approximation, but these specific points are like really mostly wrong. So maybe they're wrong, or there's some higher. But I see also in a different thing, that when you're constructing like the tree, so because you're working symbolically, the exact value where you will split, you probably have some choices. And what happened in that case in practice? Do you have, like, in practice very little choices, that the different value that will choose that will give the same split? Maybe they're very near to each other, so in which case you can say the splitting is some sort of objective, but in other cases there can be a huge distance, and in that case this kind of split is more or less you don't have much information on that. Did you look at the kind of aspects of outlier, or can that apply really in practice, or in practice it won't work because it will never happen that much?
So that's a great question. We did look into some approaches to consider outliers. And funny enough, our way of encoding things makes it easier to, maybe when we are encoding things that say, okay, these points go to left and these points go to right, you can kind of skip the well-formedness constraint for one step, to put some outlier points and direct it in a non-structured way so that it doesn't matter in the eyes of the objective. We did look into some extensions of our approach there. There were some issues in terms of the number of outliers that we were able to support. it had a pretty significant overhead on the computational cost for each additional outlier that we were allowing the model to consider. But that would be a very kind of natural extension of what you're doing here. And I think in particular, the outlier thing is the minimum depth classification algorithm and the MDMS clustering algorithm are more sensitive to that. The max accuracy, we don't need to consider anything. It just automatically ignores them. And regarding the second part of your question, it's the epsilon that we use for clustering also doesn't mean anything. Yeah, like we use it for, let's say, floating point value data sets. And for floating point value data sets, you have like 10.005 and then 10.007. And you don't want to consider those two the same thing. And even if we just use a very small epsilon that's just for floating point, well, not inaccuracies, but for minute values of floating points, it in no way affects the algorithm. And we were kind of limited to using that epsilon value. So what we produce the results is this. We normalize the features to 0 to 100, and we use an epsilon value of 0.1. So it's pretty insignificant compared to the values of the objective.
But in terms of the precision of the split, is it very narrow or it can be very wide?
It is adjustable. So it based on the domain, I would say that like if someone wants to use our algorithm in different settings, they have to look into the tree that is learned and maybe say, okay, this is it's pretty lenient towards performance, so we don't want to make a split here. But in the cases that we tested, it didn't make splits that don't make sense. It's naturally, given the objective, encouraged towards meaningful splits, and the epsilon and the thresholding part is just there to improve the performance. So that was our experience, but it can be wildly different in different settings. Thank you so much.
Yes.
Hi, thank you very much. Explainability, like say, perspective. I think from the formal side of explanation, it's a very, very strong asset that we are talking about. But I will take your point of view regarding the bridge, the gap, or what could be very important as maybe a big challenge between formal explainability and cognitive explainability, which is more and more asked for, like contents, like theory models, like not just only formal. So what's your point of view regarding this gap? What's the biggest challenge in your opinion?
It's a very challenging question.
Huge one.
Yes. So first of all, I have to do a disclaimer. My work is primarily focused on the strong notion of interpretability. My supervisors pushed me to like go work in a medical center and just try to find the applications that are like actual cases of interpretability as well, but I resisted. But it is a challenge, and I think that kind of challenge could particularly benefit from some of the flexibilities that we could benefit from in terms of using SAT. Because let's say we have the modularity of it, this kind of approach. And we also have all sorts of user constraints that can be used. I know I made a distinction here between constraints and interpretability, but in real world scenarios, it's a blurred line. All sorts of constraints can be translated into what this model is supported, and also another type of constraints can be plug and played into these kind of models. So let's say the interpretability goes down when a leaf in a node has only 5 points. That I can assume that's the case of, people do not understand what those 5 points are if it's in a medical setting. We can just get a cardinality constraint off the shelf and say within each leaf we want at least 20 points. So this kind of flexibility allows us to address very various concerns that can come in real world settings. And if we plug and play that cardinality constraint, we don't have to develop the algorithm from startup again. So again, I realize that I probably gave you a more of a strong, like, mathematical notion of interpretability again, but I think the flexibility on this side allows us to support much more on the other side and just change things on the fly that could be very valuable to, you know, a context and an application that's very heavy on knowledge, expertise, and kind of heuristics of the user.
Yeah, I understand that you are very open to this kind of rates that could be added, but as a challenge, for example, for the part for the human in the loop, and explainability, could we translate this without strings and no, excellent.
Human in the loop.
Explainability is very much one. So, how do you measure it with SAT, or we can see that with the junction with other tools?
I think my answer is yes. I think human in the loop, human can be integrated in the loop. In this approach, probably easier than a lot of others. So that's a good thing. It always begs the question of whether we need an expert on the team as well, an expert on the SAT side. The answer to that is probably yes as well. Maybe LLMs can help there. I don't know. They seem to be the solution to everything. So, but probably in my ideal case, you have an SAT expert on the team as well. But they can be. Again, the flexibility allows us to kind of adjust things on the fly and keep the expert in the loop. I think so. Yes, absolutely. Yeah. Thank you. Thank you for the good question.
We have a question online. So Julia says, what do you think about the principle of least effort in shaping representations? It implies a dependence on architecture, in practice at least. Do you think there is always dependence on architecture, or is there some underlying independent structure? The question. Yes.
So it's kind of a little bit of both. You need to know the architecture, but you need to also know the solving technology behind the architecture, and you need to break some rules. You need to encode things in a paradigm that doesn't seem to support those kind of encodings. There's always underlying independent structure. You can, well, theoretically, everything is NP complete and you can encode everything in anything. But you can never completely disregard it. And you always need to keep in mind that you need to test things out as well. I think that would be a balanced way of thinking about it. Try to reduce your problem into its core decisions. If the core decisions allow you to use some other paradigm that might not be the first thing that pops into your mind when you think about your problem, go for that paradigm, test it out, because no one is able to tell you automatically whether a paradigm is good for solving things or not. So it is a balance, but you need to push the balance a little bit. I guess that's my answer.
Thank you.
Thanks for the question.
Another question. We have a question then. How do you compare versus heuristic in case that you are not able to find the optimal solution? So you show that in case you are not able to find the optimal solution, you can approximate. So now if you want to compare the accuracy versus your approximated model versus an heuristic, how do you compare?
So there is a little bit of the fact that, well, theoretically, we might not consider them comparable because for approximation, we still have the guarantee that the solution is not far off from the optimal, but in the heuristic, we have no guarantee. But the way actually we evaluate the solutions and compare them is very problem independent as well. So for clustering, we rely on things like external validation, which is maybe not suited for classification. At the end of the day, it comes down to what our intention is with the algorithm. in many we have to be honest, I work on optimal solutions, but in many real world cases, they don't care about optimality that much. Of course, there are studies that shows optimality, particularly in compact solutions, can help us can help us not get stuck in local minima, for example, and find solutions that even for testing accuracy, which is at the end what we care about, has its own benefits. So yeah, it depends on very much on the problem. If you have some sort of external validation, that would be the way to go. But in my cases, I kind of relied on the fact that I relied on the literature that compact decision trees that are optimal are good. Let's find a faster way to learn them. So that was my attempt.
Okay, thank you. In the case of the BDD, so the ordering, you have to find the best ordering, I guess, right? To find the smaller BDD. Did you try to impose some kind of ordering in order to find the solution better?
Sorry.
If the ordering is completely free, then you have to search about all the ordering. Some constraints. Okay, I want to be this variable to be before this one. Then you reduce the size of the.
I see. That's a great idea. No, I haven't tried that. But yeah, in our algorithm, the ordering and also the ordering which can impact the size, of course, and also the accuracy, which of course can also impact the size, and also the branching, because in BDD literature, a lot of the time they focus on binary values, which begs the question, what are we talking about in terms of actual thresholds? So in our case, everything is up. Everything is free to change, and we just care about accuracy plus size with a certain weight that the algorithm tries to find. But trying to enforce ordering is, of course, another example of just being able to plug and play all sorts of user constraints. Maybe when someone wants to learn a BDD, they want the most important feature to be up there. They can just plug and play, and everything else works automatically. So another argument for modularity, I guess.
Thank you. Another question then. Did you try to apply this to learn a neural network? Like here you try to learn the smaller decision tree. You try to do the same with other models that BDD. For example, a neural network, can I learn the best or the smaller neural network that fit with my data?
Not a neural network, but I've tried to learn a kind of mathematical calculation tree where we have, let's say, like multiplication and two values. Like you evaluate each of the subtrees, you get the values, and then you use multiplication. That, of course, wasn't purely supported by SAT. We tried some sort of hybrid approach, which involved
Your shadow approach would probably
same kind of thinking, but my conclusion was that it's probably computationally too expensive so there is a balance of things that we can find in an exact and optimal way.
Yeah.
And for some cases that I tried, and maybe neural network could even be more expensive than that. But for some cases that I tried, I felt like I'm overstepping that balance.
But the neural network, you can remove the multiplication and you say, okay, I have a binary neural network like that. You don't have these multiplication questions.
Yeah, maybe that's a simplification that makes it very suitable for SAT. That would be a very good idea to explore, I think.
Anybody else have a question? More question? I give
Yes, I have a few words to say before you go for lunch. I need your attention just for 1 minute. I can't be with you this afternoon because it will be the graduation ceremony at the Faculty of Science, and 3 of my doctorate students will receive their doctorate. So I have to be with them over there. So I just want to say before I leave, there will be official closing this afternoon by the Pouya, but this is a non-official closing from my part. I want to thank all the participants, all the students involved, all the lecturers we had. I think we had a wonderful summer school because of all of you. And I want to thank our students who helped us, Jean-Vincent, Marianne, and Elise. And of course, we should not forget the most important persons, the ones of the Institute, Pierre Poirier, the director of the Institute, our secretary, Fadila, and more especially Yves Leblanc, who has been fantastic. So that's the only words I wanted to say, and thanks to everybody. It was an exciting dream come true.